Okay, so we finally made it to the last unit of AP Physics C Mechanics, right? So this is the unit known as gravitation. If you took AP Physics 1, this is a slight little review of some of the concepts that were also covered in that class. In really the difference is we're going to talk about Kepler's laws of planetary motion, and we're also going to bring in energy into this as well. Okay, so the first video here that we're going to talk about is we're going to look at the gravitational force. So again, this is probably a review for those of you guys who've taken AP Physics 1. So remember, in a universe, there is a force of gravity, right, between two masses, right? A block and Earth, a block or a block and the moon, right? So they're anywhere in the universe, right? And that's kind of the key idea is this universe, right? There's this force that it wants to bring these two objects together. So the force varies directly, right, with each of the masses. So we say the force of gravity varies directly with mass, right? So as mass goes up, force goes up. But it's inversely to the distance between them. In fact, it's going to be inversely to the square of the distance between them. So what happens is this force is what we call an inverse square law. Right, so that just means that it decreases at a faster rate than if it were just an inverse law, right? And so instead of the graph being right something that looks like this, it goes down. Excuse me, that should be right. So if it's an inverse law, it's going to kind of look, keep erasing, right? It's going to look something like this. But if it's an inverse, excuse me, if it's inverse square law, it's going to go down to zero faster, right? It's going to get towards zero. It's going to go towards infinity at a quicker pace, right? And so what happens is this is all brought together in what is called the Law of Universal Gravitation. Right? This is actually Isaac Newton, right, who did this. Now, Isaac Newton didn't necessarily discover gravity. What he discovered is that it was universal, right? So it was not just contained here on Earth, which is one of the reasons why, as we go through these videos, a lot of the equations that I write down talk about the like planets, not just Earth. Okay, and so the force of gravity, according to what Newton proposed, is that it's going to be F sub capital G is equal to G, which is known as the universal gravitation constant, times mass 1 times mass 2 divided by r squared. And r is the distance between the centers. Okay. Now, this big G has a value of 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. Now, you typically don't write that unit every time. So you could just understand if you're using this equation that if I'm using it as is, you see it on the screen here, my unit's going to be in newtons. But if I'm solving for mass, I know it's going to be in kilograms. If I'm solving for a radius, I know it's going to be in meters. Okay. So one way to think about this equation is that it's the gravitational force of attraction away from the surface of a planet. So if this is my planet, we're talking about out here, right? Not on the surface, right? The force of gravity on the surface was that idea of weight. And if you remember, the abbreviation for weight is F sub little g, right? And little g just means surface, right? If you want to think about it, right? Surface on the planet, big G means like a greater distance, right? But it does follow the law of superposition, right? So if I have multiple objects towards each other, they're going to attract each other, okay? So one thing to note is that gravity or gravitational force is an attractive force, right? Which led to Einstein talking about how love cannot be, or excuse me, gravitation cannot be held responsible for those falling in love. It's a great quote. But if you break down the way that the physics works, right, gravity is an attractive force, but Einstein is saying that you can't blame that for two people falling in love, right? So Einstein just used this gravitational concept to explain that, hey, it's not gravity that brings two people together, it's actually love that brings two people together, right? And we have to love the beauty of Einstein, when he talks, when he has quotes like that, right? And so let's look at an example with superposition, right? And so every object in a system is going to attract each other, okay? So in here it says, in the figure to the right, an arrangement of three particles, particle 1 of mass m1, which is equal to 6 kilograms, and particles 2 and 3 of mass m2, which equals m3, which equals 4 kilograms, and they're a distance a, or in some way a is going to be equal to 2.0 centimeters. So what is the net gravitational force? um, I kind of have this, it's all jumbled up here. So what is the net gravitational force F sub 1 net, right, on particle 1 due to the other particles? So we're looking for the net force on this uh, object, okay? So what happens is, if I let this kind of system play out, M1 will want to attract towards M2, right? M1 will also want to attract towards M3. So what is the net force that is acting on M1? It's going to kind of go in this direction, right? And so what I have to do is I have to find what is F1 of 3 and what is F1 on 2, right? And so this is where my equation comes into play. So I'm going to do F1 of 3 equals G M1 M3 over R squared, okay? And so I'm just going to plug in numbers. G, all right, I'll just use capital G for here. So 6 times 4 over, right, and it tells me that it's 2a away, so 2 times 0.02 squared, right? And so you do have to be careful, make sure that you convert your units to meters, make sure that you square the denominator, right? Just common mistakes. And remember, capital G has a value of 6.67 times 10 to the negative 11th. And so this works out to be 1.0 times 10 to the negative 6 newtons, right? And so it's feeling 1 point times 10 to the negative 6 newtons from object 3, okay? So now let's figure out F of 2 on 3, or excuse me, 1 on 2, right? And so again, we're going to use G M1 M2 over R squared. So it's going to be F equals G. And again, I'm just going to put G there. 6 times 4 over, now we're only a distance of a away, so it's going to be 0.02 squared. Again, don't forget to square the denominator, common mistake. So it's going to be 4 times 10 to the negative 6th newtons. Now, if you look at this, the reason why F1 on 2 is greater than F2 on 1 is, or 1 on 3, is because it's closer to F1, or to object 1, okay? Now, how do I find the net force? Well, this is acting in the x direction. This one's acting in the y direction. How do I combine them? I do Pythagorean theorem. So I do fx squared plus fy squared. Take the square root of that, and so it's going to be square root of 1.0 times 10 to the negative 6 squared plus 4.0, right, times 10 to the negative 6 squared. And that's going to give me a value of 4.12 times 10 to the negative 6 newtons, right? So now that's my magnitude, okay? And now we need to figure out the angle. And so the angle is going to be given by the inverse tangent of y over x. So 4 times 10 to the negative 6 divided by 1 times 10 to the negative 6. And we get an angle of 76 degrees above negative x, right? Because we're pointing up and to the left, it's going to be above negative x, okay? So there's your, so this is just, again, this is, this section was really a little bit of review from AP Physics 1, right? Just this equation. We just want to throw in the superposition because this is maybe a little bit newer of a concept. Okay, in the next video, we're going to look at the gravitational field, the gravitational attraction, and how does it play into really planets.